in going from permutations to combinations to polynomials, this is probably the strangest jump you'll ever experience, but it is certainly a great application of the combination formula. We're going to look at a fantastic shortcut for expanding binomials. And we actually first have to start with binomials that you can do within reason. For example, x plus y to the 0 is 1. Any base raised to the exponent 0 is 1. X plus y to the 1 doesn't change things very much. That's x plus y. And we recognize what x plus y squared is. You've done enough of that. X plus y squared is actually x squared plus 2xy plus y squared. And you probably don't have to think a lot about that. But how do you get x plus y cubed? Well, to get x plus y cubed, you actually have to multiply out 3x plus y's. We're not going to do the x plus y to the 4, so I'm going to block that out. But x plus y cubed would result from taking x plus y and multiplying it into x squared plus 2xy plus y squared, because that was the result of the previous statement, x plus y squared. So when I FOIL that out or distribute, I get x squared plus 2x squared y plus xy squared. And then I have to bring in that y, I'll change color. Then I get yx squared plus 2xy squared plus y cubed. And I collect my like terms, and I get, lost my cubed on that one. And I get x cubed plus, I should have 3x squared y's. Here's an x squared y, and here's another one, plus 3x squared y, and I also have 3xy squareds and a y cubed. Now, you can't imagine having to do that to the 4th or to the 12th or to the 17th. So we want to find a pattern for this. One thing that you might recognize in the 2 or 3 that we've done is the number of terms you get in the expansion. When I had x plus y to the 0, I got 1 term. When I had x plus y to the 1, I got 2 terms. So it seems the number of terms is always 1 more than the exponent. So the number of terms is going to be 3, 4, 5, 21. And when I look at the sum of the exponents, there's probably something you also recognize from working with polynomials before, and that is that the sum of the exponents will always be equal to the original power. So the sum of the exponents in x plus y squared, it was always 2. And the sum of the exponents in x plus y cubed was always 3. So in x plus y squared, the sum of the exponents will always be 2, 3, 4, 20. Now what's interesting is if we write out the numbers in the expansion in a triangular format, actually, because it actually is a nicer way of making the connection. So when I had x plus y to the 0, that was a 1. X plus y to the 1, my coefficients were just 1s. I'm going to transfer that over here. We just did x plus y squared. It was 1, 2, 1. And x plus y cubed is 1, 3, 3, 1. Now remember how you're recording your answer. You're recording your answer in descending powers of x. Record answer in descending powers of x. That's how this has a pattern. That's our standard form. So this is 1, 3, 3, 1. And if you follow the pattern that we've seen before when we were working with pathways, you can see that this 2 arises mathematically from 1 plus 1. This 3 results from 1 plus 2 being 3, 1 plus 2 being 3. So on the outsides, I continue to have 1s, but on the inside, I get a 4 here, a 6 here, and a 4 here. 1 plus 3 is 4, 3 plus 3 is 6, and 3 plus 1 is 4. And that pattern is obvious here. 1, 1, 1, 1, 1, 1. And 1 plus 4 is 5, 4 plus 6 is 10, 4 plus 6 is 10, 4 plus my 1 on the outside is 5, and my 1. So using this triangular expansion, there are, when I'm expanding and I'm talking about my exponent being n, there are always n plus 1 terms in the expansion. The sum of the exponents of x and y in each term is equal to n. The exponents of x decrease term by term from n equals 0, and the exponents of y increase term by term from 0 to n. The coefficients in each expansion form a symmetrical triangle, and we can continue that triangle, and we'll take some opportunity to do that. Let's slide down. So we've got the first number of rows of Pascal's triangle, and then we're asked to expand that using the pattern that we've talked about. So remember, Pascal's triangle is built upon the binomial multiplication of x plus y to the n. I'm going to create some new rows. What do they look like? 1, 6, 15, 20, 15, 6, 1. That's the expansion associated with 6. And associated with 7, what would those numbers look like? 1, 7, 21, 35, 35, 21, 7, 1. So now that I have the expansion for x plus y to the 6 and x plus y to the 7, I can actually do my expansion of x plus y to the 6 and write out what it would be. So I simply copy my coefficients and play around with my exponents, x5, x4, x3, x2, x1, x0, and y1, y2, y3, y4, y5, y6. So x plus y to the 7 would follow those same numbers. Which row of Pascal's triangle is equivalent to the coefficients of the terms in the expansion of? Now you have to remember how the row arrangement is related to the exponent arrangement. The row arrangement and the exponent arrangement is plus 1 because we start at 0. So x plus y to the 6th is actually the 7th row. X plus y to the 7th is actually the 8th row. X plus y to the 12th is actually the 13th row. And x plus y to the n is actually the n plus 1 row. And again, that's because we start at 0. So now I actually get to build the 8th row. 1, 7, 21, 35, 35, 21, 7, 1. And now I'm looking for those the first terms, both in Pascal's triangle numbers, which I recognize now as 1, 7, 21. But it's actually related to combination form. Pascal's triangle can also be created by the choices. Pascal's triangle is actually based upon the combinations, the number of different ways we can multiply x's and y's together. So for example, to get the second coefficient here, I have 3 different binomials to choose from, and there's only one combination that's going to give me the first term. Only one set of variables that will give me the first term. So I can write the 8th row in terms of combinations. So the 8th row starts with 7, choose 0, 7, choose 1, and 7, choose 2. And I can keep exploring that 8th row of Pascal's triangle. I've got it in Pascal's triangle form, but I can also recognize it in terms of combination form. By the time I'm looking at the last combination, I've got 7 choices, 7 binomials to choose from, and 7 of them communicate. I have to make a choice of all 7 to get the last y. It's the 8th in this case. So just reinforcing the habits of Pascal's triangle. If I'm looking at 4 choose 2 and 4 choose 3, which is from the 5th row in Pascal's triangle, they will actually add to be the same as 5 choose 3. And I'll do that same circling and identifying. So 6 choose 0 and 6 choose 1. 6 choose 0 and 6 choose 1 will give me what part of 7. And we can follow that same general pattern down. Another interesting pattern is the summing of the coefficients. What's really interesting about that? Well, let's take a look at the sum of the coefficients. In row 1, they sum to 1. In row 2, they sum to 2. In row 3, they sum to 4. In row 4, they sum to 8. Is there a pattern? So you can add up those coefficients. I did the first 3 or 4 and then finish off the last 2. It's interesting that they're actually related to powers of 2. 2 to the 0 is equal to 1, 2 to the 1 is equal to 2, 2 squared is 4, 2 to the 3 is equal to 8. Well, we can generalize. The sum of the coefficients of row n would be 2 to the n minus 1, and if I was looking at n plus 1, it would simply be 2 to the n. It's always 1 less.